Question 15. A spring is stretched to a length of 5.4 meters along the floor. So here's your spring. This is 5.40 meters. Oops, meters. A 1.32 meter long pulse. So here's the pulse, and it's 1.32 meters. So that's your wavelength. Travels from your hand to the fixed end of the spring and back to your hand. So it goes here and then back. And the time that it takes to do that is 1.96 seconds. How long does it take the pulse to reflect from the fixed end of the spring? So you have to ask yourself, what is this question asking? It's asking, so here's the pulse, it travels this way, it gets to the end of the spring here, and then it reflects or it inverts. So to do that, and then travels back along the spring upside down. The question is asking, how long does it take to do this? In other words, what is the period of the wave? And to find the period of the wave, if we use the universal wave equation to find the frequency, we can then find the period. So, to find out the frequency of the wave, we have the wavelength already, right here, the 1.32. We need to find the velocity. The velocity is actually fairly straightforward because we know that the pulse goes 5.4 meters this way and then 5.4 meters back. So it travels a total distance of 10.8 meters, and we know it does it in 1.96 seconds. So that will give us the velocity, which will be 5.51. And then we can plug it into this formula here to find the frequency. And finally, we can invert that to find the period. And that will give you the answer of B. Numerical response, number 1, another vector question. Again, I cannot stress the importance of knowing how to add vectors using components. Oh, I forgot to solve that one earlier with the cosine law. Never mind. Maybe this one will solve with the cosine law. Anyway, this is really important for physics 30. You have to be able to do this. An airplane flying with a velocity of 900 kilometers. Now, I changed this on the test. I just forgot to change it here, and we changed it to north 30 degrees west, which is 120 degrees, and 190 should be expressed as west 10 degrees south. Okay. So the plane is flying in that direction, experiences a wind blowing in that direction, and we want to know its resultant. And again, we'll start off with a little sketch. So north 30 degrees west is approximately like this. There's your 30 degrees north and then 30 degrees towards the west, and that's 900. And the wind is blowing at 50 kilometers per hour, so much shorter vector, and it's west, start at west, and then go 10 degrees towards the south. So it would be something like that, maybe actually shorter. Yeah, quite a bit shorter. Should be even shorter than that. Anyway, that's, you get the idea, and that's 50 kilometers, and here is your resultant vector. And so you can see your resultant vector is going to be less than 900. Because this red vector goes slightly down. All right, so now that we know that, we should get that slightly less than 900. we can separate each vector into components. That's not very nice. And you use cosine and sine, you should be really proficient at this, so I'm not going to go through the details. And so you're going to use sine to find out the x value, and the x turns out to be 450 kilometers per hour, and the y turns out to be 779.42. Let's go to at least 2 decimal places here so we're accurate. Okay, so that's for the plane. Now for the wind. And again, use sine and cosine, and note that your wind is going west and south. The plane was going north and west. The wind is going west and south, and for that one, we get an x value of 49.24. And a y value of 8.68. So we'll call that step 1, separate into components. Step 2 is going to be to add the components and then make a new triangle. So your total x All right, we've added the x's and we've added the y's, and notice you have to be very careful about the signs. The x's were both in the same direction. They're both west, so therefore they're both positive, or they're both negative, as long as they're both the same thing. The y's, we've got north, the plane's going north, but the wind is going south, has a southerly component, so one has to be negative. And now that we've got that, I'm just going to do it over here. We can make a new triangle with those components. So we've got, and I always do my horizontal component first. So my horizontal component is 449. My vertical component is 700. 440. 770.24. Right angle triangle, and use Pythagorean theorem to solve for the resultant vector. So that's going to be the square root . And you end up getting 892, which we predicted it was going to be a little less than 900. So that seems right. And then make sure you write it in the correct format, which is 8.92 times 10 to the exponent 2 kilometers per hour. So your answer for that question would be 8922. Now, if you did want to solve this one using just the cosine law, so let's go back to our diagram right here. This one's a little tricky. It requires you to think a little bit. What you need is this angle in here. Okay, and we know, well, we know that this angle in here, this little guy here, is 10 degrees. And we know, look, if I just draw this here, this is 30 degrees. Oh, this is going to be a hard one. So that's going to be 30 degrees in here. All right, yep. And then this is 10, and we draw a straight line down there. That's going to be 30 degrees in there. That's going to be 10, and that's going to be 80 degrees in there. So in other words, if this is 80 here and this is 30 here, then that's going to be 110 degrees in total. And so if you're using the cosine law, the cosine law says that c squared equals a squared plus b squared minus 2ab times the cosine of c. So in this case, it would be the 900 squared plus 50 squared minus 2 times 900 times 50 times the cosine of 110 degrees. And if you plug that into the calculator, hopefully you'll get exactly the same thing that we just got. 900 squared plus 50 squared minus brackets 2 times 900 times 50 times the cosine of 110 degrees, end of brackets, and then square root that, and you get slightly different answer. And that's just because of the rounding off. So that's the way that you would do it if you were using the cosine law. All right. Next question. The magnitude of Jupiter's gravitational field strength is 26.2. The magnitude of the gravitational field strength of the radius were increased by a factor of 4, and the mass were doubled. Great ratio question. We're talking about gravitational field strength. Here's the formula for gravitational field strength. And again, it's a relationship question. The relationship is that the gravitational field strength is directly related to the mass and inversely related to the radius squared. So in this case, it says the radius were increased by a factor of 4. So we're just going to put a 4 squared down there, and the mass were doubled. So we're going to put a 2 there. And we get that. So in other words, the gravitational field strength is going to change by a factor of 1/8. And then we can just take our 26.2, multiply it by 1/8 and get the new gravitational field strength. Of 3.28. Yeah, pretty straightforward. And before you do that question, before you do the question, try and think it through in your head a little. If you take Jupiter, which has a huge gravitational field strength, but you increase it, and you increase the radius by a factor of 4, so it's 4 times bigger, but then you double the mass. Given the squared relationship, it's probably the gravitational field strength is going to decrease by quite a bit. Okay, 18, 19, and 20. Can we get through these? And let's do it. A child in a merry-go-round. Okay, now this question again has some typos in it. So it's just saying that this is the velocity. So you're dealing with circular motion. This is the velocity, and this is the radius. The one on D2L has the mistakes corrected. And the question, so your child on a merry-go-round is riding on a horse that is 2.6 meters from the center of the merry-go-round. If the horse has a velocity of 3.25, then the frequency of the merry-go-round is, so what we're going to have to do here is first calculate the period and then change that to frequency. Solve, take your formula, 2 pi r over t, solve it for t, plug in the radius and the velocity, and that will give you a period of, turns out to be 5.03 seconds, but they want the frequency, and the frequency is always the inverse of the period. And that's going to give you a frequency of 0.199. Okay, pretty straightforward question. 19, a mass is attached to a spring with that constant. The amplitude of the oscillation is 15 centimeters, then the magnitude of the maximum acceleration. So what do we have here? We have the mass. We have the spring constant. And we have the displacement. The question is asking for acceleration. So masses on horizontal springs, we should know that the restoring force equals the net force. And once you've got that, it's a simple plug the numbers in and solve, and you end up getting an answer of 36 meters per second squared. And the last one, oh, the last one's a gift. It's very easy. A sound wave has a speed, so it gives you the velocity of the sound wave. And it gives you the frequency of the sound wave. And it's asking you for the wavelength. There's the universal wave equation, solve it for wavelength. And that yields an answer of 1.31 meters. That's it. That's the end of the practice final, and good luck on your final exam.